Have you ever stopped to think what's actually happening inside a database that's built for today's world? I mean, we're not talking about your simple spreadsheets anymore. We're talking about systems that have to handle just massive amounts of complex and, honestly, pretty messy data. So today, let's pull back the curtain on the architecture of a really popular modern database, MongoDB, and see if we can answer the one question that kind of started it all.
Right? This is the big one. See, traditional databases, they love neat and tidy rows and columns. But modern apps, they're all about data that's constantly changing, evolving. So how on earth do you build a system that's flexible enough for developers, but also powerful enough to run at a global scale? Well, the answer starts by completely rethinking the most basic building block. Instead of a rigid row in a table, MongoDB's whole foundation is something called the document. The best way to think about it is like a flexible, self-contained file. It's designed to mirror how developers actually think and code, with objects and data nested inside other data, all neatly organized in one place.
Okay, so let's actually build this architecture from the ground up. We're going to start with that single document and see how it all logically scales up into an entire database. It's actually a pretty simple hierarchy when you break it down. You've got your individual document, which is technically a BSN record. Think of that as a sort of binary supercharged version of JSON. Then you group related documents into a collection. This is kind of like a folder. And the magic word here is Schema-less, which just means the documents inside don't all have to look exactly alike. Super flexible. Finally, you stick all your collections inside a database, which is basically the main filing cabinet for your whole project. So that's the blueprint, the logical organization. But where does all this stuff physically go? I mean, where do these documents and collections actually live? Let's jump from the data structure over to the hardware. Everything runs on what we call a node. And a node is really just a server, could be physical or virtual, that's running an instance of MongoDB. But here's the really crucial part. In the real world, especially in the cloud, you almost never ever rely on just a single node. Why? Because if that one server fails, poof, your entire app is down. And that's exactly why we group them into a cluster, where a whole team of nodes works together. All right, let's do a quick recap before we move on. So at the data level, we have documents living inside collections. On the physical level, we have the servers, our nodes. And when we group those nodes together, we create clusters. Now, these clusters come in two special flavors we're about to dive into, Replica Sets and Sharded Clusters. This little table gives you a fantastic overview of the whole stack, from one tiny piece of data all the way up to the system that runs it. And this brings us to the two biggest headaches for any serious database. First, how do you keep things running when hardware inevitably fails? And second, what do you do when your data gets just way too big for any one machine? This is where the magic of MongoDB's architecture really starts to shine. Now, what's really key to understand here is that MongoDB uses two different tools for these two different problems. For safety and keeping your app online, it uses Replica Sets. That's all about making identical copies of your data. But for handling massive size and getting more speed, it uses sharding, and that's all about splitting your data up. Two totally different problems, two purpose-built solutions. So let's tackle safety first. A replica set is, at its heart, all about redundancy. It's a team of nodes, usually 3 or more, that all hold an exact, up-to-the-minute copy of the very same data. The goal is super simple, no single point of failure. And here's how it works in practice. Your application sends all its new data, all its writes, to one node that's designated as the primary. The other secondary nodes are just sitting there, constantly watching and copying every single thing the primary does. Now, if that primary node suddenly crashes, maybe the power cord gets kicked out, the secondaries notice instantly. They hold a super fast election, pick a new primary from among themselves, and your app just keeps on chugging along, often without anyone even noticing there was a problem. That is high availability in action. Okay, so replica sets totally solve the safety problem, but they've got one big limitation. Every single node in the set has to hold a full copy of all the data. So what happens when your data set grows into terabytes or even petabytes? It gets way too big to fit on any single server. I don't care how powerful it is. And the answer to that problem is sharding. It's a total paradigm shift. Instead of copying the whole data set over and over, you split it up. You divide and conquer. Each shard is actually its own little replica set, so it's still safe. But here's the key. It only holds a piece of the total data. Maybe one shard holds user accounts from A through M, and another one holds N through Z. Of course, for a system like this to work, you need something to manage all the moving parts. First, you have the shards themselves, holding those slices of data. Then you have the config servers, which act like the master map for the whole system. They know exactly which piece of data lives on which shard. And finally, you have the query router, also called mongos. This thing is the traffic cop. Your app talks to the router quickly checks the map on the config servers, and it sends your request to the exact shard that holds the data you're looking for. Pretty slick.
Okay, so we've built up this complex, super resilient architecture. What's the big payoff here? Why go through all this trouble? Well, it all comes down to one of the most powerful ideas in modern computing: horizontal scaling.
You see, in the old days, if your database got slow, you had to scale vertically. That meant throwing out your old server and buying a bigger, faster, and way more expensive one. It's like replacing your car with a giant truck. But MongoDB's architecture lets you scale horizontally. When you need more power, you don't replace anything. You just add more cheap, regular servers to your cluster. It's like adding more cars to your fleet instead of buying one giant bus.
And this, right here, is the ultimate takeaway. This ability to scale out horizontally just by adding more nodes makes MongoDB a perfect match for modern cloud platforms like AWS, Google Cloud, or Azure. Do you need more capacity? You literally just click a button, spin up some new virtual servers, and add them to your cluster. It is flexible, it's cost-effective, and it is built for the elastic, on-demand nature of the cloud. So, as we wrap this up, you can see how this whole architecture of documents, replica sets, and sharded clusters provides a really powerful answer to that first challenge. It's built for the messy, modern world. Which really just leaves one last question for you. In a world where data growth feels pretty much infinite, is your architecture ready for it?